So this is Beyond MISI Part 2, and we have quite a few good talks and getting into some glacial stuff, which I deeply care about as well. Oh, by the way, my name is Atsu Muto from Temple University. Some of you might not have recognized me because I have this pandemic ponytail, but it's still me. Okay, right. So, well, let's get right into it. The first talk is by Golledge, and this will be online. And this is on marine ice cliff instability.
Good morning, everyone, and thanks for the invitation from the organizing committee and from Peter for the invite to give this presentation today. I'm sorry I can't join you in person. Always enjoyed WAIS workshops in the past. Unfortunately, the world we live in, it's not quite as easy as it used to be. I would have joined you virtually, but it's about 2 a.m. my time, so you'll forgive me for sending a pre-recorded presentation. But anyway, hopefully I'll have something of interest, or at least something that will stimulate some discussion amongst yourselves. Now, I apologize for using some British idiom in the title. If you're not familiar with the phrase taking the mickey, maybe you could look it up or ask somebody near you, and they might explain it for you. Anyway, what I'm going to talk about, of course, is marine ice sheet retreat in the context of WAIS, and particularly in terms of the marine ice cliff instability hypothesis. So let's start with the recent IPCC AR6 report that came out just in August. And what we can see when we look at the sea level projections from that are clearly that the largest source of uncertainty in terms of global sea level rise this century and the next is the large uncertainty associated with the behavior of the Antarctic ice sheet. So the graph here from chapter 9, basically showing what's going to happen or what could happen over the next century and a half. We've got a fairly tightly clustered set of emissions scenario dependent pathways there in the sort of colored envelopes. But the things that are really kind of jumping out are these, the dotted line and the dashed line there, which are showing the low confidence scenarios, but the low confidence but high magnitude scenarios. That's the key thing. And the thing that is important in this context is that those low confidence, high magnitude scenarios basically result from a single process and in fact a single model, which is of course the DeConto and Pollard model with marine ice cliff instability. So it's worth exploring where that hypothesis has come from, what underlies it, and thinking a little bit about how and why we need to incorporate it. So we're probably all very familiar with it, and I don't want to teach you suck eggs, but it's worth recapping. Basically, MISI comprises two components. First of all, we need ice shelf hydrofracture. We need ice shelves to basically disintegrate virtually instantaneously. We need them to collapse very, very quickly. And then once that's happened, the theory goes that the exposed ice cliff at the grounding line will then, under certain circumstances, be prone to structural failure because it's too high. Now, whether or not that all plays out, we don't really know. We don't have many places in the world where this kind of thing happens. There are some small examples in Greenland and some of the outlet glaciers where cliff collapse does occur. And of course, we've seen some of the smaller ice shelves in Antarctica disintegrate through hydrofracture. But when we're thinking about the large ice shelves, so Filchner-Ronne and the Ross ice shelves, you know, these are ice shelves that are about 1,000 kilometers across in some cases, and hundreds of meters thick, you know, 700-800 meters at the grounding lines. That's a vast amount of ice. So to get a process that basically allows all that to disintegrate in a short space of time is something that we need to look at very carefully, I think. But the question I'm posing here is, do we actually need it? Do we need to have this Mickey scheme? Now, if we go back to the beginnings, to the Dave Pollard et al. 2015, basically the reason that this scheme was invented was because when they were running simulations of past warm periods, in this case warm Pliocene periods, they were unable to get sufficient ice out of Antarctica, particularly out of East Antarctica, to satisfy the reconstructed global sea level budget. So trying to find upwards of 10 meters out of East Antarctica was too much of a challenge for their model at that time. So what they say in the paper is that we need to assume there are other physical processes at play, and that seems a fairly reasonable approach to take. Now, in the 2016 paper, I'm using this example because it shows the comparison between the two sets of physics. This is now a warmer than present scenario, but not Pliocene. This is last interglacial. And those two circular panels at the bottom show the difference between their old model physics on the right-hand side and the new model physics on the left-hand side. And you can see there that in the old scheme, even with identical climate forcing, they were getting only 1 meter of sea level equivalent last interglacial. Under the new scheme, they were getting 6 meters. So quite a big change. And you can see there the top panel there, the top graph. Basically, this was their justification, showing that their graph of mass loss, the red and blue lines for 2 different initial conditions, they basically sort of are pretty close to the black line, which is Bob Kopp's probabilistic reconstruction of the Antarctic ice sheet contribution during the last interglacial. But let's look a little bit more closely at where that comes from. And if we look at that top panel on the right-hand side, this is my quick plot of the forcings that Rob and Dave used for these simulations. So it's a sort of transient run that uses imposed temperature anomalies for 5,000-year periods, which are sort of updated every 5 Ka. And you can see there that they start their run at 130 K and they impose an instantaneous warming of nearly 2 degrees in the ocean and the atmosphere. And then that sort of gradually declines through the interglacial period. And you can see that the mass loss pattern basically follows the shape of these forcings. But there's 2 things to note. Firstly, at 130 Ka, they're starting their simulations cold. They're imposing a step warming of 2 degrees in the ocean, or 1.7 degrees in the ocean, and about 2 degrees in the atmosphere. So basically, that very steep line in the top right, the top left sea level plot that they're showing, even though it looks quite similar to the one from Bob Kopp's reconstruction, albeit slightly offset by a couple of thousand years, the rate of change there is really just a response to this imposed rapid warming. You're taking a cold ice sheet and you're hitting it with 2 degrees of ocean heat instantaneously around the entire continent. Of course, it's going to lose a lot of mass very quickly. So it's not really reflecting the true evolution of an ice sheet coming out of a glacial period where the imposed forcing would be much more gradual. So that's one thing to note. The other is that the inflection you can see there in the top left-hand side panel, where there's a sort of kink in the blue and red curves at about 115 K, that is exactly where the forcings go negative. And it's only one of the forcings that go negative. It's the atmospheric anomaly. So basically the ocean is still warmer than present, so it should still be contributing to sea level rise. So the reduction there is really only coming from that imposed atmospheric cooling, which is kind of interesting. Now, when we look at the earlier paper, the 2015 paper, we can see how these 2 different mechanisms, the ice cliff failure and hydrofracture, actually play out. The blue line, the pale blue line, shows what happens if you have neither. The dark blue line is if you just have the cliff failure. And of course, with just cliff failure, it doesn't do anything because the ice shelves are still there. You need the hydrofracture, the green line, in order to expose those cliffs. But it's only when you have both the hydrofracture coupled with the cliff failure that you get that red line, the big mass loss. So the problem that I'm sort of wrestling with in my head is that the ice sheet model that they previously had just basically wasn't very sensitive to either atmosphere or ocean, whereas in the new setup, it's very sensitive to one or other of these forcings. But the new mechanisms that they've built in basically just depend on water depth and for the cliff failure and surface melt for the hydrofracture. That basically means that ocean thermal forcing has been thrown out the window. There is no real role for ocean heat in this scheme at all, or no more than there was previously at least. So the huge increase in sensitivity is basically because they've devolved responsibility for the retreat from the ocean to the atmosphere, and the atmosphere now has to do all the heavy lifting in terms of driving retreat. This, to my mind, goes against present-day observations. We just don't see that big of a forcing of Antarctica from the atmosphere because it's still too cold. It may have been more sensitive to the atmospheric warming in the periods of the past when it was warmer, and it may be in the future. But we're going to have to warm up the atmosphere a lot to melt large portions of the surface of the ice sheet. So basically, there's no modern analog, and that's something that Rob and Dave are pretty open about. There is no comparison there, nothing to work from. So the key question is, can we get the same response, the same high magnitude contribution to sea level for those paleo constraint periods in other ways? And I'm obviously just going to show our own attempts to do this. We basically, these two panels both show the same warm Pliocene period. They're both 5,000-year runs using a fixed climate forcing. Rob and Dave's on the right-hand side, they get just over 11 meters. As on the left-hand side, we get just over 10 meters. So less than a meter difference, sea level equivalent between the two. You can see the pattern of mass loss is actually quite similar. We don't lose as much from aurora as they do, but it's actually pretty similar overall. Now, we don't have any ice cliff collapse in there. We don't have an accentuated atmospheric forcing. This is driven mainly by the ocean, and we're using a subgrid grounding line melt scheme to basically get the ice sheet to be more sensitive to the ocean. And again, we can see that with last interglacial simulations, they get around 4 meters, or they did in the previous or the current paper, we get around 4 meters in our latest paper, different pattern of mass loss, but basically the same ruling paradigm as is all coming from the ocean. Theirs is coming basically from the implicitly atmospheric forcing. Now, our approach has been criticized. They've basically said that it's questionable on physical grounds. And of course, our counter to that is that actually when we do these simulations, we tune the models specifically to reproduce not just the net mass balance, but actually the different components of the mass balance. So we're matching to the brown rectangles in each of these panels, and we're, surface mass balance, we're definitely in the ballpark. Basal mass balance is the key thing. We're hitting that pretty closely, short time period, of course, in terms of the constraints we have. But the point is, if our scheme was that hideously inaccurate, then we wouldn't be getting anywhere near that. And actually, we've put a lot of work into getting exactly the right kind of melt field for the continent and the right kind of sensitivity. So we feel like the scheme is justified. So we can argue a lot about whether the MICI scheme is right from a process perspective, and there's lots of exciting work coming out of the community, and many of these papers and others that I haven't cited here are probably going to be talked about at this meeting right now. Lots of good stuff looking at this problem from a process perspective. How do we actually simulate this process reliably? For me, the big question really is just about this distribution of responsibility of forcing from the ocean to the atmosphere. Are we happy to do that? Does that make sense from a glaciological perspective based on what we know about WAIS? So that's the question in my mind. It'll be really interesting to hear thoughts on that and hear where people are going, what the community feel for this is. But I think one thing that's clear is that for the next AR that's going to come out of IPCC, we're going to need as a community to present some kind of MICI MIP. There's going to be some model into comparison project that can evaluate different representations of this scheme to understand not just the reliability of the model, but the bounds within which it operates and the uncertainties that go along with that. So I'll leave it there. I'll thank you again for your attention. I hope it's been interesting. I'm sorry I'm not online to take questions right now, but feel free to flick me an email if you're interested, and I hope to hear from you soon. Enjoy the rest of the conference. Thank you.
Okay, so we'll take the questions at the end of the session, at the end of the discussion time. So we'll move on to next talk, which is by Eliza Dawson on the basal thaw. And I'd like to note that all of the presentations in the rest of the session are by students. So please, if you're judging, please enter the scores. Okay.
Hi everyone, I am Eliza Dawson. I'm a PhD student at Stanford University working with Dusty Schroeder. Today I'm going to be telling you about my recent work investigating basal thaw as a driver of mass loss across Antarctica. And this work is also in close collaboration with Winnie Chu, Eliza Mantelli, and Helen Sarosi. So across Antarctica, mass loss is driven by a warming climate, and this causes thinning or disintegration of ice shelves, increased discharge of upstream grounded ice. So understanding processes that contribute to mass loss is really important in the context of predicting future sea level rise. So building off the talk just before me, I want to now focus your attention to the upstream grounded ice, and in particular to the ice bed interface. And I want to ask the question, could the grounded ice basal thermal state evolve? And if so, would this impact the ice sheet mass balance? So on the left here, I have a plot of pressure-adjusted basal temperatures that I modeled in the ice sheet and sea level system model. In red, you can see places where the bed is at the pressure melting point, so it's thawed. And you'll notice that that roughly lines up with places that have faster flowing ice. So these are glaciers, ice streams. On the other end of the spectrum, you can see in the continental interior and in the transantarctic mountains regions where the bed is very frozen. It's very cold there, and these are also slower flowing areas. What I think is really interesting, though, are these regions where the bed is frozen but near thawed. These are the regions that I show in yellow in the pressure-adjusted basal temperatures. So in order to investigate how basal thawing could change and whether thawing could impact the ice sheet, it's really important to find these thawable bed regions. So I am using thawable bed to define regions where the bed temperature is just below the pressure melting point, but close to thawing. So the first step that I did to investigate thawing is use ISSM to model basal temperatures, as I showed before. But then I also applied a mask to focus on regions that are near fast-flowing glaciers and near regions where the bed is thawed. So I wanted to find regions that are frozen, but near thawing and within 100 kilometers of places that are thawed, because these are most likely the regions that we could foreseeably see thaw in the future. The next step that I did was look in these regions, which I'm calling the experiment zones, to see how much of the bed is actually in this thawable category. So the two plots that you can see on the right are the extent of thawable area, the spatial extent in West Antarctica and in East Antarctic drainage basins. You can see that in West Antarctica, the basin with the most amount of thawable area is the Amundsen Sea sector, and in East Antarctica, this is the George Fifth Land region. And now the next component in actually simulating thawing is to be able to capture somehow the role of thawing in reducing friction at the bed and actually permitting faster sliding. So you can see a Weirtman friction law, where alpha is the basal friction coefficient. This is a model inferred value that is derived from inverting for that parameter by matching the model and observed surface velocities. And here I have a plot of the basal friction coefficient that I derived for the entire continent. Now what I did is I grouped the basal friction coefficients into categories that correspond to frozen, thawed, or thawable bed regimes. Each plot here is a drainage basin of Antarctica. The blue regions are West Antarctica, the green regions are East Antarctica. And you can see each line is the CDF of what the basal friction coefficient values are where the bed is in one of the 3 thermal regime categories. What you'll notice is that in all of these basins, thawed is less than thawable, which is less than frozen. And this finding is really useful for being able to set up experiments to simulate thawing. So here's an example of how I actually prescribe thawing in my experiments. This is just for one sector. Let's say in some region, the thawable bed friction coefficient value is 100. The corresponding thawed value, I would then be able to find to prescribe a new friction coefficient. So this is effectively simulating thawing by reducing the friction coefficient value at the bed. So now if I apply this to all the drainage basins across the continent, first look at the table that I have shown. I do 4 experiments. Experiment 1 has the smallest category of what I'm defining as thawable bed. So just within 2 degrees of the pressure melting point, up to experiment 4, which is regions anywhere within 12 degrees of the pressure melting point. In those regions, I use the method I just described to prescribe thawing to those thawable regions by changing the friction coefficient. Then I run each of these experiments forward in ISSM for 100 years and compare this to a control simulation with no changes to the friction. What you'll see is that for all basins, there is mass loss. This is most extreme for experiment 4, less so for experiment 1. And I think that this finding is really interesting, that it's consistent across all basins, but also I want to draw your attention to these 2 regions that have the most mass loss. So if we dive a bit more into these regions, it's Enderby Land in East Antarctica and the George V Land region. And these regions are experiencing high mass loss, 1, because they have large thawable areas, and 2, because there's a large change in the basal friction coefficient associated with thawing. And I think these regions are really interesting because they kind of bring a new element to maybe what we think of as typical areas that are losing a lot of mass. Right now, this is all in West Antarctica. But this result has shown that there's some areas of East Antarctica where the bed is frozen but close to thawing. And if a mechanism were to increase the bed temperature by just a few degrees, it's possible that these regions could be necessary to add into the picture of continent-wide mass loss. And also the bottom plot that I show is just to see that the order of magnitude of mass loss that I'm getting is roughly comparable to current observations, but obviously this would be in new areas. So I just wanted to now leave you with just a little teaser into some of the next work that I'm doing. I can't end a talk without having a little bit on radar, so the next area that I'm going is to look more into really asking the question, can we constrain the spatial pattern of frozen, thawed, and thawable using radar? So can radar be a tool to better constrain what my model results are showing for where the bed is near thawed? And can radar help us identify by looking at radargrams and analyzing the bed reflectivity and other properties to better look at where these transitions might be and aid in more modeling in the future. Thank you, and I look forward to talking to you more in the discussion.
Okay, so next up we have Jeremy Brooks talking about subglacial abrasion.
Hello, everyone. My name is Jeremy Brooks. I'm a graduate student at the University of Wisconsin-Madison. I'm here to present the results of some research done with Dougal Hansen and Luke Zoot. So the aim of this project is to quantify the percent of basal sliding energy that's dissipated through subglacial abrasion using some different laboratory experiments. So first, I want to motivate what this research is about and hopefully why it's important to you. During the process of abrasion, when a glacier slides over a hard bed, some clasts held in basal ice erode the base of the hard bed underneath, and that has substantial rock-on-rock friction that affects the basal drag occurring at the base of the glacier as it moves over a hard bed. So hence, because it affects basal drag and friction, it affects sliding. And sliding laws, which relate basal shear stress to the sliding velocity of the glacier, typically don't include this rock-on-rock friction. Typically, they just assume that the ice is clean at its base and doesn't have basal debris. And it's really important to have well-constrained physics of these sliding laws, because the choice of sliding law, which relates to the shear stress to sliding speed, can really affect ice sheet modeling results. And looking at the transient forcing of Pine Island Glacier or Thwaites Glacier to changes in climate forcing over the next few centuries, those results are sensitive on the sliding law used, so it's important to dive into the physics of what's happening at the base of the glacier. It's also important for understanding rates of glacial erosion. So this equation is just that A dot is abrasion rate, and then it's equal to some parameter K times debris concentration C, and then also multiplied by basal shear stress and sliding speed. So that parameter K is dependent partially on the percent of sliding energy that's dissipated by abrasion. So if you want to look at long-term evolution of subglacial topography, it's important to have good constraints on the abrasion law being used as well. So in the 1970s, a couple studies were published that looked to quantify the percent of sliding energy dissipated by abrasion by studying alpine glaciers, as well as some laboratory studies of rock friction, and they put an estimate of about 30% of sliding energy being dissipated by abrasion. But due to some limitations in their methodology, as well as some variety of assumptions used in their work, that's a very poorly constrained estimate. So that motivates our work, which is to use more cutting-edge laboratory techniques and apparatuses to constrain the percent of sliding energy that's dissipated by abrasion. So I also want to talk a bit more specifically about West Antarctica and why this work is important for that. So recent data from the GHOST project that looked at seismic and radar data for transects underneath Thwaites Glacier found that there is substantial bed heterogeneity. In particular, there are some regions on the Stoss side of basal highs that are composed of hard beds interpreted to be exposed bedrock, and other regions that are soft deformable beds. And that's important because both the basal topography and the rheology of the bed can greatly affect the stability of the grounding line by affecting the transient response of Thwaites Glacier or other analog ice streams. So it's really important to have good constraints on the friction occurring at the base of the glacier because it affects sliding laws, which then affects projections of grounding line stability and sea level rise. So now I'll talk more about the particular experiments we did. So we used two different shear apparatuses, the first of which is a direct shear, which is shown in the schematic here on the left. So with this, we take a sample chamber that's 10 centimeters by 10 centimeters in width, which is shown in the picture on the right, and we fill granitic clasts and then freeze it in with ice. Then we place it in the sample chamber and apply a normal load on top of a limestone bed so that the ice with basal clasts is in contact with the limestone bed under a normal load. Then we can slide the sample chamber above the limestone bed at a prescribed velocity, which simulates the process of abrasion. So the granitic clasts dig into the limestone bed and produce striations just like actual glaciers do. We also have LVDT sensors, which record the vertical and horizontal displacement. We have a load cell to keep track of shear stress throughout the course of the experiment. And then we also have a heating plate at the bottom of the apparatus, which we can use to vary the melt rate, which controls the contact force between basal clasts and the bed underneath. So using the direct shear, we conducted 9 experiments, sliding granite clasts over limestone beds And then we varied normal stress and the melt rate to control sort of the amount of abrasion occurring in these experiments. So the next shear apparatus we used is the ring shear. So this is a larger scale device. It's similar to the direct shear in principle, but instead of having just a rectangular sample chamber, we have a larger cylindrical one that spins in a circle, so it allows for continuous displacement and much longer duration experiments. So in this, we can also apply the sample chamber under a normal load, where it grips the top of a ring of ice that has granitic clasts in the bottom, and then we slid it over a marble bed in these experiments. We also have a circulating fluid bath on the outside of the sample chamber that we use. We can vary the temperature of that bath, which makes sure that the ice is kept at pressure melting temperature throughout the course of the experiment. So we have a torque sensor to record shear stress with this apparatus. We apply a normal load, and we also have an LVDT sensor to look at the vertical displacement occurring throughout it. So we conducted 2 different ring shear experiments where we had granitic clasts sliding over a marble bed, and we varied the melt rate, which controls the contact force between the experiments. So at the end of the ring shear experiments, we can take out the marble bed, which looks like this, and then on the right, hopefully you can see we have some striations in the marble bed that are white lines that are kind of following the curve of the marble. So for the marble beds and the limestone beds from the direct shear experiments, we have all these striations produced. So our next step is to use an optical profilometer to scan those striations. Essentially what it does is it scans the striations at a high vertical resolution and produces DEMs, like in the picture you see on the left. So we do that for all the striations in each of the experiments. We can sum up the volume of those striations to get the volume of abraded material, the volume of abrasion that occurs in these experiments. So next we have to calculate the surface area of that material and use that to estimate the abrasion energy expenditure. So to do so, we have to produce some rock flour using the direct shear and then measure its grain size distribution and then apply this equation shown here, which looks at the grain size distribution, assumes that the particles are spheres, but then applies a roughness factor R to sort of match it with the actual surface area, knowing that the particles are actually spheres. So then we take that surface area produced from that top equation, then use it in the bottom equation by multiplying by the surface energy, which depends on the rock, either limestone or marble, and then that gives us the energy dissipated by abrasion throughout this process. And then the last step is just dividing that value by the basal sliding energy, which gives us the percent of sliding energy that's dissipated by abrasion. So that was our methodology for these experiments. And now I'll show you the results. So this is a plot of basal shear stress on the x-axis versus the percent of sliding energy dissipated by abrasion on the y-axis for all the direct shear and ring shear experiments. And what we found for all of these is only about 1 to 5% of the sliding energy is dissipated by abrasion. That's substantially lower, about an order of a magnitude lower than previous estimates from the 1970s. So this shows that a much smaller proportion of sliding energy is dissipated through the rock-on-rock friction occurring during abrasion. So next, we can also plot basal shear stress versus what's essentially total abrasion on the y-axis, and we find that there's a very strong correspondence between basal shear stress and the amount of abrasion occurring in these experiments. So that's an important result because it sort of verifies using experiments the abrasion law proposed by Halley in 2011, where basal shear stress is one of the variables controlling the rate of abrasion. So now just putting these results back in context for ice sheets, this shows, so this work constrains the percent of sliding energy that's consumed by abrasion, which can help improve our understanding of the physics controlling friction at the bed of glaciers and hence improve sliding laws. So we find that it's a relatively small percent of sliding energy that's dissipated by abrasion, which hopefully means that we don't have to, the rock-on-rock friction occurring at the base of a glacier isn't perhaps so important for these sliding laws. So this also helps us constrain the parameter for the abrasion law, which is really important for modeling the long-term evolution of subglacial topography, either for studying paleo ice sheets or potentially very long-term projections on the evolution of ice sheets and glaciers as well. So this is all important because recent data from the GHOST project shows that there's lots of bed heterogeneity and basal topography underneath Thwaites Glacier and other analog ice streams. Therefore, it's important to look at all of the physics involved with that mixed basal rheology. So thank you all for listening, and I look forward to your questions at the end of the session.
Okay, we move on to the next talk. And next talk is still staying on the topic of the basal processes. It is by Dougal Hansen. Dougal? And he'll be talking about frozen fringe growth.
Hello, my name is Dougal Hansen, and I'm a PhD student at the University of Wisconsin-Madison, working with Luke Zoot. And today I'm going to talk about some recent, very recent experimental results we've done in collaboration with our Colin Meyer and Alan Rempel. As part of a larger NSF grant, I'm interrogating the physics controlling sediment entrainment and the growth of frozen fringe at the ice bed interface. So what is frozen fringe? So simply put, it is an ice-saturated layer of basal debris that's accreted to the base of glacial ice where it's in contact with unconsolidated sediment. So as you can see on the cartoon on the left, this frozen fringe layer is a three-part mixture of sediment grains that are enveloped in some mixture of liquid water and ice. And importantly, such layers have been observed directly in West Antarctica, as you can see at the sequence of photos on the right showing the transition from clean glacial ice at the top to this debris-rich layer at the bed, about 0.72 meters thick in this photo. So given the large spatial extent in West Antarctica, where it's inferred that subglacial till rests in contact with glacier ice, it's likely that frozen fringe is a ubiquitous feature with obvious implications for overall sediment transport rates or sliding dynamics. So factors such as the spatial extent of fringe or its rate of growth or its thickness all could be potentially first-order controls on catchment-wide erosion rates or the deposition of sediment at the grounding line of ice sheet or ice streams, which can impact that ice sheet stability. So in order to predict these variables, though, it kind of requires some ironclad constraints on the physics that's governing sediment entrainment, of which there are currently two competing theories, regulation infiltration or pre-melting theory. So the classical interpretation is that ice infiltrates sediments through the process of regulation. So essentially, ice in contact with sediment grains melts in zones of elevated pressure, and that meltwater percolates through the pore space and then refreezes in the lee in zones of lower pressure, which then releases latent heat. And this, out of this comes this relationship, so shown here, where this rate of infiltration is essentially a function of the apparent conductivity multiplied by a pressure gradient in this frozen layer. And while this model has been used to varying degrees of success to predict fringe growth, it neglects some significant complexities that are undoubtedly present in nature, including pre-melting, the effects of curvature in the pore space, or wetting. And importantly, it assumes that the pressure difference, or that the ice pressure and liquid pressure is in equilibrium, which is often not the case at the ice bed interface in nature. So two factors, I see that the format got a little messed up here. So two factors that can contribute to this departure from bulk equilibrium is one, you have a thin layer of pre-melted film that separates ice from sediment grains, and the disjoining forces in this pre-melted film can cause a departure from equilibrium between the ice pressure and liquid pressure, and that effective stress can then be transferred through that film from the ice to the sediment grain. And then secondly, curvature within the pore throat can cause a departure as well, and in order for ice to infiltrate this pore space, this pre-melting theory would suggest that it's dependent on this critical entry pressure, which is essentially the ratio of 2 times the ice-water surface energy divided by the radius of curvature of this pore throat. If the effective pressure is less than this critical entry pressure, which is shown by this cartoon in the center, you essentially get sliding at the interface, although ice might be able to drag along that top layer of sediment grains. And if ice, the effective pressure is greater than this critical entry pressure, as shown on the cartoon on the right, then ice is able to infiltrate the pore space, and you get this frozen fringe. So plotted here is the scaled fringe thickness on the y-axis versus the effective stress scaled by this critical entry pressure. And just a quick, the thing to take away from this really quick is that the steady state growth of a fringe is going to be dependent on the effective stress and the melt rate, and that fringe growth can be stable in melting conditions. Other factors that might be controlling fringe thickness over time is effective stress, so there's a positive scaling relationship between the two. And then there's an inverse scaling relationship between fringe thickness and then the pore throat radius, or the melt rate, or the apparent conductivity. So to test these, the validity of these theories, we grow fringe in this cryogenic ring shear apparatus that Jeremy described previously, with key differences that we're pushing that ice under pressure into a bed of sediment. And then we're also monitoring deformation in the sediment throughout the experiment using cameras that are photographing the bed through clear acrylic walls. And for this talk, I'm just going to be presenting the results from 2 recent experiments with contrasting grain size distributions. So we did one with an Iowa Luss with a roughly log normal grain size distribution, and then we did another one with a subglacial till. So desired outcomes of what we're kind of hoping to achieve with this is to grow fringe in the laboratory kind of under these prescribed conditions, and then compare them to the model predictions of both pre-melting theory and regelation infiltration. And we do this using the experimental boundary conditions. And then we also estimate, key sediment properties using a Monte Carlo technique. There's a typo here. That should be 2020 in that citation. And then we plug these parameters into basically the theoretical, the theories that have been developed by Algonkian, over the years. And then finally, we're also going to shear this sediment bed following the growth of this fringe in order to assess the influence that the presence of frozen fringe might have on both the frictional response of the system and the character of deformation that we observe. So here's an experimental time series from the first experiment, which was the Luss. And so the general protocol for these experiments is that we would load up the bed under pressure, shear it until the deformation reached a steady state, and then we would stop the motor, so we'd stop the ice ring spinning and hold it under pressure for some prescribed period of 10 days to 2 weeks to allow the fringe to grow, and then we'd start it up and start shearing it again. In this experiment, we missed the final shearing phase because of a malfunction with our RAM, but nevertheless, you can see the evolution of these various experimental evolution of these various experimental parameters. On the right, at the top, you have a constant ice pressure, and then effective stress plotted below it, and then the second plot is the basal shear stress, and then the third plot's the friction, and then finally we have the average water pressure at the bottom. Here are some photographs of the ice ring following the experiment. So you can see a layer of frozen fringe or partially frozen fringe that's been accreted to the base at that ice bed interface with some spatial heterogeneity in thickness. But generally, on average, we measured an approximate thickness of about 1 centimeter, which is shown in this photo on the right. The plot on the left takes the predictions, or the transient fringe growth for regelation, infiltration, and also pre-melting theory. And that star represents where our observation kind of falls in line. And while there's about a factor of 3 difference from our observation with the predictions of our model, it's far closer and much stronger fit than this 2 order of magnitude difference that we'd expect if regelation infiltration was in controlling that sediment entrainment. And one factor to note here is this is quite recent data. I got this, we pulled it out of the ring when I was in the field. I just got back from the field 2 days ago. And so we're using some best estimates for certain physical properties that we will continue to constrain. And as we constrain these better with various empirical relationships, we will probably see that fit start to improve. All right, so moving on, this is a similar time series except for the subglacial till. And the key takeaway from this is that we see similar friction at both stages. So in the initial shearing phase, when fringe growth is, the presence of fringe is either very minimal or non-existent, and then following the end of the experiment where the fringe is well developed. And the takeaway with that is that, this in conjunction with the visual record, which shows these well-developed shear bands, we interpret this as that grinding mechanics are dominating the system, and that shear is being accommodated at the base of this frozen fringe layer. Here are some photos of what the fringe looked like in this till experiment. In general, there are some key differences between both the ice saturation within the pore space, and also the way that you had this clumpy material adhered to the base of this fully ice saturated layer. And this is something that we're going to continue to explore with further experiments. More of just an interesting motivation is to move forward. And finally, we use a digital image correlation to capture the displacement fields. And from that, we calculate these mean horizontal flow profiles for both the deformation in the initial shearing phase with no to minimal fringe, and then the final phase, in the presence of a fringe. And this sort of zone where you have a constant velocity, that's essentially where ice was stuck in the wall of the ice at the boundary. So that's representing the speed of the ice moving forward, and that inflection point moving from that that constant area of velocity, that represents where you start seeing that deforming layer. And with a fringe here, there is about a 40% difference in the width of that deforming layer, but they're both really on the order of about a centimeter, just a little over a centimeter. So really subtle differences, in the sediment flux. Okay, so just a few takeaways from this. Pre-melting theory from our observations is a much stronger approximation for the sediment entrainment rates under our experimental conditions. Also, the fringe character and degree of saturation is markedly different between the two grain size distributions. And then finally, even in the presence of fringe, that forward motion was being accommodated by a shear band, sort of at its lowest extent. But anyways, thank you, and I look forward to your questions.
Thanks, Dougal. Next up, we have Nate Stevens, and he will give us some insights from alpine glaciers.
Should just be full screen.
Oh, yeah, I'll go to view. Let me actually do this. Yep, yeah, it's okay. Yeah.
All right, there we are. Hello, everyone. I'm Nate Stevens. I'm the end-of-year triple header of Zoot Lab graduate students. So thank you, Atsu, for abbreviating my unfortunately long title. But we'll be getting into some of these short-term processes that might matter in the long term. And I'll run you through a few observations and ideas that we have on it. And this has been a collaboration both with colleagues at the University of Wisconsin, which occupies Ho-Chunk land, and colleagues at Penn State University, which occupies Susquehannock land. So we also have support coming from NSF. My work has been heavily funded by the ITGC GHOST project, so I have been productive with those things, as well as a lot of support from UW-Madison, Penn State, Iris Pascal, and several other people and organizations. So the motivating question with all of this, as I alluded to before, is, well, short period meltwater supply dynamics. So we're talking changes in meltwater supply to the bed of a glacier occurring over hours to days, and the impact on sliding dynamics impact the long-term stability, talking years, decades, and longer, for ice sheets in warming scenarios. And so we're going to use a series of analog sites, both two alpine glaciers, one in Canada, one in Switzerland, as well as a number of glaciers in Greenland, land terminating glaciers along the western Greenland margin, as well as Helheim to give us at least a little bit of taste of a tidewater glacier and how it might relate to, at the end, Antarctica. And so to take the picture, we'll start off with 1 year of what water and sliding does. And so we have this cartoon from Davison et al., 2019. And so we start off with this meltwater supply through the year. We start with low meltwater going into high meltwater and reducing down again at the end of the melt season, so this blue curve going across. And what the sliding does in response is we initially start off with some background winter velocity, this black curve, and then there are a series of these spikes in velocity which correspond to things called spring events. So these are abrupt increases in basal water pressure as the subglacial hydrologic system is inundated by these waters and is overwhelmed by them because it is not yet adapted. But at a certain point, we wind up having an abrupt drop down towards average overall velocities, so this late melt season period. And what that corresponds to is the establishment of efficient drainage systems, these channelized features, Roethlisberger and Nye channels, for instance, that effectively drain the bed, suppress those spikes in water pressure, and reduce that sliding velocity by increasing drag on the bed. And so if we go to the western Greenland margin, we can take a look at anomalies in both the sliding velocity, or the overall velocities, which largely comes from sliding, so this top figure, as well as the meltwater supply, or anomalies in the meltwater supply, which is this figure below, and this is from this Williams et al. Review in 2020. And so what they found is that for a period where there are warmer conditions, this produced more meltwater overall, so a higher meltwater supply on average, year over year. This corresponded to an overall deceleration of these land-terminating margin glaciers. But then there was a period of cooling following that, less meltwater supply, and this corresponds to a speed up in the overall glacier flow. So this is interpreted as an increase in sliding speeds. So we have this inverse relationship between water supply and average sliding velocities that if we go back to our cartoon, these warmer conditions correspond to an extension of these periods where we have these well-established subglacial drainage channels. And so we get more of that late season flow style. But if we have less meltwater, it constricts that period. We have shorter lived and later forming drainage channels. And so you get a slightly higher velocity in those cases. This is where it gets interesting. So in 2019, we went out to Saskatchewan Glacier, and we took some measurements of the surface velocities there. We constrained the geometry of the glacier. And then we had the good luck that there are a lot of surface DEMs of the ice reaching back into the 1940s. And so we took those and we said, okay, what is the internal deformation velocity doing for this glacier if we use the very simple Glenn's flow law? And so that's what this light blue curve with circles is going on below. And we compared that to both survey and satellite observations, which are these triangles and squares. And what we found is there was a separation between the surface velocities and the internal deformation velocities proceeding from the 1950s, when Mark Meyer initially characterized mostly internal deformation, very little sliding, that we have an increase in basal sliding. And as we all know, in this period, from the 1980s onwards, we've largely experienced warming. And so we have the result that from Saskatchewan Glacier, we have climate warming corresponding to more sliding, contradictory to what we were seeing for the western Greenland margin. We then go to Haut-Glacier d'Arola over in Switzerland, and we can see a bit of this same behavior occurring, again, in the same period, that there's a greater separation between the surface velocities, the black line, and the internal deformation velocities, that blue line. And the reason why Haut-Glacier d'Arola is such a nice place to look at this in greater detail is because they have 46 years of continuous discharge measurements from it. So we can understand what is the short period hydrology doing. And so this is a summary from these two papers, Gebhardt et al. And Lane and Nenow. And what we see is that during this enhanced sliding period, we have an increase in the variability of daily discharge. There's a bigger range between the high discharge and the low discharge of a day that's concentrated in that late melt season when things should be quiet. But if we look early in the melt season, there's not much change in that variability. So this got us thinking. We have these two observations. So we have land-terminating glaciers on the western Greenland margin that are slowing down with more meltwater. We have two Alpine glaciers, at least, that are speeding up sliding when we increase meltwater year over year. So we have a contrast here, and we need something to explain it. And this is where the short-term behaviors start to become interesting and important. We go to the modeling from Schoof 2010, and what he did is he imposed meltwater pulses into the system and looked at the response of both the hydrologic system and the rates of sliding for theories of the time. And what the big upshot of this was, and this was being done on ice sheet scale models, is that by introducing these pulses, these short-term high variability periods of meltwater supply, it increases the sliding velocity. So now we might have something to explain what we see in these two Alpine glaciers. And so we go back to Haute Glacier d'Arolla when we have our cartoon from earlier of our general hydrologic season. And what we have in this enhanced period is we may have a transition from the smooth curve to we have higher variability for our meltwater curve, which then introduces more high velocity periods during for the sliding late in the melt season, increasing the overall annual velocity. And so if we continue to warm, even if the variability in the temperature driving meltwater supply remains the same, if we have a higher mean temperature, we might get more melt with each of those day-night cycles. And so these are these short-term processes that might become important as we ramp across years, decades, and onwards. And so then we go back to the Saskatchewan Glacier, where unfortunately we don't have this rich record of 46 years of discharge, but what we do have is high-resolution observations from our time out there in the late melt season in August of 2019. And we see there is variability in, or there's very clear diurnal cycles in the meltwater supply, so that's that top figure, or that top trend line. And beneath it is the surface velocities we observed with an on-ice GPS. As you can see, the periods of high meltwater variability correspond to high velocities. We have 5-fold increases from background, the background velocity a little bit below 50 meters per year for several of these days. And then when we go into lower variability, these crank back down. So this is contradictory to that initial picture that we wind up with low velocity variability late in the melt season. So what does all this all mean for WAIS? I'll need to connect it back because this is indeed the WAIS Workshop. And so if we look at temperature variability for Antarctica, as we've been talking about in these previous sessions, it's generally too cold in Antarctica right now to produce melt in large places. We don't have quite the same conditions that Greenland is starting to be subjected to. But what we do have is looking at the past 2 decades of daily temperature range, we do have similar temperature ranges to these Alpine glacier sites. We're looking sort of in this 6 to 10 degrees C range. And that proves to be sufficient to force these transient features for sliding that seem to be what's driving this speed up in sliding over decades. And so for all of these glaciers I've been talking about thus far, they've been land-terminating glaciers. As we all know, Antarctica is mostly drained by tidewater glaciers. And so does this actually matter once we look at tidewater glaciers? So I'll leave you with the idea of at least there is some evidence coming from Helheim, this study by Davis et al. From 2014, that recovered a non-tidal diurnal cycle in the velocity. So this would be related to changes in the meltwater supply through days. So this might indeed matter for tidewater glaciers as well. So in conclusion, we have some evidence from these Alpine glaciers that this increased variability in meltwater supply drives increased sliding speeds. The Alpine systems that we've looked at are in this window, this mean temperature that's sufficient to get that variability produced in the meltwater supply, but these polar regions might not yet be susceptible to it. And so it wouldn't be a Zoot Lab presentation without us saying, we're working on some of these questions right now, trying to understand the physics by running these variably loading experiments in the ring shear, so those will be coming up. And there's been some recent advances with a paper just out by Victor Tsai and others that puts a physics-based numerical model to actually addressing these transient sliding features. And so I'm looking forward to having discussion and questions at the end of this. Thank you.
Okay, next talk is by Paul Summers, and he will be giving one through the video. And he'll be talking about the migration of the shear margin on thwaites.
Hello, my name is Paul Summers, and today I'll be sharing with you research we've been doing investigating the potential for inwards migration of the shear margins at Thwaites Glacier in response to thinning. Much research has focused on Thwaites Glacier and the greater western Arctic ice sheet and the degree to which they're vulnerable to the marine ice sheet instability. The marine ice sheet instability is driven by monotonically increasing ice flux through the grounding line as the grounding line retreats inwards. This classic conceptualization of the marine ice sheet instability is based on flowline modeling, which neglects 3D effects, including the effects of changes in lateral drag. One such 3D effect is that changes in ice stream width could break the monotonic relationship between grounding line flux and the grounding line position. An illustration of this is shown here, where uniform thinning of the ice sheet changes the driving stress and geometry of the ice shelf. As the driving force is decreased across the ice stream, we see this change in force balance can impact the shear margins in this illustration, bringing the shear margins inwards. With this mechanism in mind, we set out to answer the question, how will the shear margins at Thwaites Glacier respond to thinning in the coming decades? To answer this question, we developed a 3D depth average thermomechanical free boundary model that solves for both the ice velocity within our domain as well as the position of the shear margins within our domain. As input to this model, we apply multiple ice surface geometries to represent different thinning scenarios, as well as different bed strength configurations to investigate the sensitivity of our model results to the particular distribution of bed strength beneath Thwaites Glacier. Shown here on the left is our model domain on the lower Thwaites Glacier trunk. Our lateral boundary conditions are set to stress-free boundary conditions, and our upstream and downstream boundaries are set to constant velocity boundary conditions that are set by surface velocity measurements from the measures data set. And our nominal grid spacing is 6 kilometer spacing. Jumping right into our results, in the interest of time, we're only going to show one case of bed strength today, and that bed strength configuration is going to be the inversion of bed drag using ISSM, which was made available through the init-MIP effort. For this scenario, we'll consider 3 different thinning scenarios, that of 25, 50, and 100 meters of uniform thinning across the entire ice sheet. And the 4th case we consider is that of no thinning, which is the ice sheet geometry that is observed today. Shown here are our model results for all 4 of those cases, with the ice speeds shown as well as the margin position in dotted lines. For ease of comparison, we've also plotted the differences in ice speed between each of the thinning scenarios and the control case of 0 thinning. From these results, we see that there is significant shear margin migration, particularly on the western shear margin, for the more extreme thinning scenarios, that of 50 and 100 meters of thinning. In particular, in the 100 meters of thinning scenario, we see inwards migration of the shear margin all the way to this mid-trunk slowdown that is observed today that coexists with a basal high point beneath the main trunk. However, when we look at the most modest thinning scenario, that of 25 meters of thinning, we do not see significant migration of the shear margins, which is consistent with the relatively stable observations of the shear margins in the satellite record. However, we do see that the distribution of slowdown of surface velocity in response to thinning is relatively asymmetric, with most of the slowdown concentrated on the western half of the main trunk. And so the question becomes, how does this compare to observations of surface velocity at Thwaites Glacier over the past decades? When we look in the satellite record, we see that there's good data for 2014 and 1996, and when we look at the speed differences between these 2 periods, the largest offset we could find with high-quality velocity data for our domain, we see that the overall signal is that of acceleration, which is, at first look, inconsistent with our model results, which showed deceleration across the model domain. However, this acceleration is thought to be driven by ocean forcing and calving effects at the coastal margin, mechanisms that are not accounted for in our model, and so it's not immediately surprising that our model does not reproduce the acceleration signal observed in the record. However, where the satellite record observations and our model do agree is the pronounced asymmetry of the signal, with there being significantly less acceleration on the western half of the main trunk. And although far from conclusive, we see this as consistent with our model results in that this asymmetry of signal could be generated by a combination of more uniform acceleration of the ice sheet due to ocean forcing at the coastal margin, and in combination with the asymmetric slowdown due to thinning over this time period. And so in this way, we view the observation, the asymmetry that is present in the satellite observation of speed up at Thwaites Glacier over this time period as consistent with our model results, in particular, our most modest thinning scenario. In conclusion, we find that inward shear margin migration is projected in response to the ongoing thinning at Thwaites Glacier over the coming decades. However, significant uncertainty still remains into the exact nature of this shear margin migration, in particular, whether the eastern or western shear margin migrates first, and the degree of thinning that is necessary before we begin to see significant shear margin migration depends sensitively on the bed strength profile beneath Thwaites Glacier. Thankfully, through the International Thwaites Glacier collaboration, there are numerous field efforts that are currently working to better constrain basal conditions across the basin. In particular, the TIME project is focusing on the eastern shear margin, which will provide valuable constraints on basal conditions there, as well as make very fine measurements of any potential migration of the shear margin that might currently be occurring. And additionally, the GHOST project and their traverses will provide valuable feedback or valuable constraints for the along flow and cross flow variations in basal conditions. So we look forward to getting the results from these field campaigns soon and hopefully be able to incorporate them into our modeling in the near future. And with that, I'd like to say thank you.
Okay, so the last talk of this session is by Seth Olinger. He'll be talking about the seismic signatures of rifting on Pine Island Glacier ice shelf.
Hey everyone, I hope you like my Steve Jobs sweater. I got it just for this talk. But it's a pleasure to be here at my first WAIS conference. My name is Seth Olinger. I'm a fourth-year PhD student with Brad Lepofsky and Maureen Denol at Harvard and the University of Washington. And this work was also done in collaboration with Brendan Crowell, who helped us process some GPS ice velocity data. And so I'll tell you a little bit today about my investigation into seismic signals generated by rifting on Pine Island Glacier and what we've learned about the physics of the rifting process from those seismic signals. So it turns out that rifting is hard to study. As you know, about half the ice mass lost from Antarctic ice shelves is accommodated through calving. And many of the largest icebergs that calve off of Antarctic ice shelves happen when large cracks called rifts propagate across ice shelves. And when tabular icebergs calve, they can reduce the contact area with, between the ice shelf shear margin and the bedrock in the nearby embayment, reduce buttressing, and then cause acceleration of the glacier. And so in order to better understand how that process progresses, we really need to understand the physics of rifting. But it turns out that rifting is hard to study. There are a few ways that we can get continuous in time observations that allow us to really monitor the progress of rifting, and satellite imagery really offers us a sort of few-day recurrence interval at best. But it turns out that seismology is a great way to do this. Seismology, particularly multi-year passive deployments of seismic instruments, allow us to make continuous in time observations that can track the progress of the rifting process from initiation, propagation, and potentially the calving as well. And so in this work, we do just that using seismic instruments that were deployed on Pine Island Glacier. So in 2012, there was a small array of seismometers and GPS instruments that were deployed on Pine Island Glacier ice shelf for 2 years. You can see where they were deployed. As in many ice shelf seismic arrays, it was sort of an unfortunate geometry for the types of inverse problems we like to use in seismology, but we do the best we can. And so that array was deployed in January of 2012. And then in May of 2012, a second branch of this rift that already extended across the ice shelf opened up, which I've highlighted in red there. And then in November of 2013, the next year, the large iceberg B31 had calved off. And then the instruments were retrieved in December of 2013. But it turns out if you take a closer look at the imagery that's available from Pine Island Glacier during that period of time, you can find these two images recorded by the Terrasar X instrument. And so the first one is from May 8th, 2012, and you can see there's a small crack extending from the shear margin, but it's not otherwise notable. And then just 3 days later, on May 11th, that crack is extended nearly 7 kilometers to meet up with the main body of the rift. And so you can see here, the second branch of the rift is outlined in maroon there, and it was previously arrested along a basal trough, which I've put a dotted line along. And then it extended, presumably within only that 3-day window, about 7.5 kilometers, which to my knowledge is one of the largest single episodes of rifting that we've observed. And so naturally the next step was to look through the seismic data and see if there was a signal during that duration of time that we might think corresponded to the rifting that we've observed. And so if we do that, there's one really big signal in that time period. So what I'm showing you here is a vertical velocity seismogram recorded by one of the instruments on Pine Island Glacier from May 8th to May 12th. And there's this one really large long duration signal that happens during that period of time, which I've highlighted in pink there. So if we zoom in a little bit, we can see some pretty interesting characteristics of the signal. I'm not showing you the entire length of it here, but it has a duration of nearly 2 hours, which is pretty long. And it also features these really long period oscillations that you can see there at the end of the record, with periods of almost 5 minutes, which we interpret to be the bobbing up and down of the entire ice shelf, basically, in response to fracture. And it's also a really dispersive event, which means that different frequencies travel at different velocities. So you can see at the front of that record, there's all these really high frequency little wiggles, and then the low frequencies arrive later. And that's a characteristic of many wave types that allows us to interpret something about them. And so even though we see this one huge rifting event in the data set, it turns out the actual forward propagation that resulted in the calving is much more likely to be accommodated by small fracture events, because we don't see many, many kilometer scale fracture events. So the next step was to try to look for many of these smaller events using the characteristics of this big one that we found. And so we do that. We designed a detection algorithm based around the dispersion that we observe in the canonical May 9 riftquake, which is what we're calling them. And we find about 50,000 other events that have very similar characteristics. Much shorter in duration, though, and as a result likely correspond to much smaller portion of the ice thickness breaking. And so what I'm showing you here is basically the entire catalog. On the top panel, plotted in black, are all 50,000 events with a low transparency, so you can sort of see where they overlap. And the average waveform is plotted in blue. The 3 panels left to right are the vertical north-south horizontal and east-west horizontal components of the seismogram. And then in that bottom panel is just the same events that you've seen plotted in black, but plotted as rows with red pixels representing positive amplitude and blue pixels representing negative amplitude. And so what you can take away from this is they all look really similar, which is super cool and indicates that they're likely generated by sort of the same set of source physics. And that's great in terms of trying to interpret these and in terms of trying to draw conclusions about whether or not they've been generated by the same processes. And so now that we have all these events, we can try to figure out where they're actually coming from. And so we do that by calculating back azimuths using the polarization of horizontal waves. So we can calculate essentially the angle from which these events arrived. And so in maroon there, I'm showing the back azimuth that we calculate for that May 9 event, which again corresponds to the maroon Thanks, everybody. Sorry about that. We're back with a new battery. So yeah, the maroon ray there corresponds to that May 9 event, which one supports the hypothesis that that signal we recorded was in fact generated by fracture along that part of the rift, and also sort of tells us that our method might be working because it's sort of pointing where we think it should. And so among the 50,000 catalog events that we recorded, you can clearly see that there are 2 main source regions. There's the northern shear margin, which is shown in purple, and then the rift tip region, which is shown in orange. And now that we've sort of teased out which of these events are coming from which spot, we can look at the temporal distribution of when these things occurred based on their spatial cluster and see if we can learn anything about how the rifting process actually progressed in this case. So here's a couple time series. In black, you're seeing a ice velocity curve basically derived from the GPS instruments. And then in purple, you're seeing the time series for the shear margin events, and in orange for the rift tip events. And so notably, there's not that much activity that happens at the rift tip in 2012, which corresponds to a relative lack of development at the rift tip zone in imagery through that period of time. But in 2013, both the rift tip and the shear margin really pick up in activity following this surprisingly rapid drop in ice velocity that happens in about May of 2013. And this data does not allow us to actually interpret what that is. Best guess maybe could be something to do with regrounding, because that's an important control on ice velocity at Pine Island Glacier. But what we see is that there's a pronounced change in ice dynamics, and the fracture that we see sort of responds to it. So it's really interesting to note that this suggests the stress concentrations that drive rift fracture are sensitive to the background stress field of the ice shelf. And so finally, we model the some of the catalog events to see whether or not we understand what types of waves are actually being generated here. And so we do a really simple sort of one-dimensional approach in which we have a floating beam, and we force it with a bending moment. And we think that a bending moment gets applied during fracture, basically due to the imbalance between the ice overburden pressure and the buoyancy sort of up the ice column. And I'll take any questions on the more specifics of this later. But it turns out this really simple floating beam, which is only one-dimensional, infinite in length, and doesn't take into account any of the huge heterogeneity of the ice thickness at Pine Island Glacier or the important boundary conditions, actually does a great job of capturing some of the sort of first-order characteristics of the observations. So in orange here, I'm showing one particular large observed seismogram, and then in blue is the model. And so we've modeled here both the vertical component velocity seismogram and the radial horizontal component, so the horizontal component that's polarized in the direction of propagation. And as you can see, it does a pretty good job, especially for such a simple model. And the type of wave that's generated by that model that we showed is a flexural gravity wave. And so what have we learned? Well, we have the first continuous record of kilometer scale rifting, which is really exciting. And we've learned something about the types of waves that are generated by rifting, because our model suggests that flexural gravity waves are the type of wave that are generated by rifting. And the timing of these events also suggests that fracture at the rift tip corresponds to changes in ice dynamics. And the next step, which we've done some preliminary work with, is to use a Monte Carlo inversion to explore the parameter space for our model. And the preliminary results of that sort of suggest that event durations on the order of seconds to tens of seconds best explain the observations. And that tells us that the fracture process, we think, is happening basically on the order of seconds, which supports the idea that rifting is probably a brittle elastic process, and that linear elastic fracture mechanics is likely an appropriate way to model rifting moving forward. So that's all I've got. Thank you very much. I appreciate it.
Okay. Okay, so that is the end of the talks for this session. So could we have the speakers come up to the front, and we can move into the discussions. And I think Paul Summers is online. I don't think Nick Golledge is online, unfortunately. Okay. And if you have questions, please come up to the front and ask the question. I think we're down to one microphone, so I'll just run around. Huh? Yeah. Okay.
Great talks, everyone. My question is for Nate. I'm wondering if you could talk a little bit about the bed properties of the systems you were looking at, and thinking about like saturation rates of the sediment, and if you think that is heavily involved in the sliding events that you were seeing.
So with each of the systems that we looked at, or at least the two Alpine systems, they're both hard-bedded glaciers, and so we're sufficiently away from the toe that we think it is largely till-free. That's with a big asterisk, because at least with the Saskatchewan Glacier, no one's drilled to the bed. Out Glacier de Rolla, I think, is better characterized, so I don't think there's so much sediment working. For the Western Greenland margin, a lot of the times it's assumed to use hard-bedded sliding laws. So I haven't thought about it too much from the side of what are the subglacial sediments doing, because they're certainly there in some concentration.
Okay. Yeah, thanks guys, and shout out to all the students. That was awesome. My question is for Jeremy about your experiments. So people who use like marine sediments, to understand past ice behavior and dynamics, we often look at grain size as a really good proxy for like distance to calving lines or ice margins. But it's harder to infer things about like basal conditions and things like that. So I wonder if from the results of your abrasion experiment, you mentioned that you looked at grain size parameters of the like rock flour products. And so I wonder if there's any like kind of diagnostic things that you learned from your experiments that could help inform, people who do paleo work to like better interpret past basal characteristics?
Yeah, so we didn't go into that in this talk, but we have looked at the grain size distribution at varying shear stresses and produced from both limestone and marble. I know Dougal has looked at that data, and I think there's some slight dependence on grain size distribution on basal shear stress, but it's kind of a work in progress that we're still like assembling all the data, gonna produce more rock flour and analyze the grain size for that. So potentially.
We actually have another question for Jeremy online. So Tim, please go ahead and speak up.
Hi, can you hear me? Yes,
We
all right.
hear you.
Yeah, I see the chat. I want to thank you for the very interesting talk and also about introducing me to the concept of abrasion. I mean, I never really thought that something like that could be happening or that it would be important at all. I'm an ice modeler, so I've been working a lot with basal friction laws for the past weeks and months. And I'm wondering a little bit like can we, because you showed us a formula with this A is K times C times tau B times UB. And I'm wondering a little bit like, because that's apparently how you calculate the abrasion energy, but can be in some way reverted so that you can incorporate it in, so to say, in your basal friction law, that you also like take into account in your basal friction law that there is abrasion energy being lost, so that there would probably be less that there would be less energy left for sliding in that sense. Maybe we can discuss that a little bit. Like how can you shape your work into a more ice model friendly version?
So I had some trouble hearing the question, but I think it was about how to incorporate like abrasion or rock friction into a basal sliding law.
Yeah.
So there's been some work done that it basically incorporates the vertical melt rate as one parameter that could be included there. I think it was a paper in like 1988 by Shoemaker that looked at a model including that, because the vertical melt rate, like the vertical component of the velocity, can control the contact force, which is related to abrasion. But I don't think it's been very explored since then.
Can you again, or put maybe in the chat the name of the paper?
Sorry, what was that?
If you can repeat the name of the paper or put it into the chat.
Oh yeah, the paper is by Shoemaker from 1988. I don't have the title, but I can communicate with you offline if you'd like.
Sure. Thanks.
Yeah, great talks, everyone. My question was initially for Eliza, but I realize now that it could open a broader discussion for all of you that do the ice bed interface analysis and stuff. So I was curious if there's been any evidence of like basal warming to the point where some of these places could become thawed, and if there's any ice sheet wide variability in the types of processes that you think might cause that.
Yeah, great question. I think this is where some of the radar analysis could potentially play a role and be an interesting component to look at. One area that I think could be interesting would be looking at ice rises and trying to look at more of the basal thermal history in these areas, because there's some places there that we think the bed has been thawed and then transitioned to frozen. Granted, that is the opposite way, but that's still a way to kind of get at maybe there's some changes there, such as the Bunyan Stock ice rise and then Institute ice stream right next to it, and maybe that has a role in thermal changes. But yeah, I think like down the line, as I kind of identify some more areas in my modeled basal temperature that could be thawable, then I am excited to kind of dig into a lot more radar data in the area to try to figure out if we can strain what the temperature is, and then maybe even be able to look at archival radar data sets and compare to modern. Does anyone else have something to add? Okay.
So thank you for your talks. My question's for Jeremy, actually. Is there a particular reason you use marble? Oh, sorry. Is there a particular reason you use limestone and marble in your experiments? And then, somewhat related to that, do you think the different types of lithology under the ice will affect these abrasion processes?
Yeah, so to answer the second part of that question, I definitely think the different lithologies would affect it because the hardness contrast between the granitic class and whatever the underlying bed is a very important property for abrasion. So we're actually conducting some more experiments than what was shown in the presentation that varies the lithology of it. And the reason we chose marble for those large ring shear beds is because we needed like a countertop manufacturer to make it. And people make marble beds, but not like sandstone or whatever. So that sort of limited our choice of lithology. We're hoping to get more beds with different lithologies to further examine the importance of that.
I would just add too that the marble versus granite like maximizes the hardness contrast, so you can like sort of put an upper bound on the energy expenditure. And granite on granite in like under those conditions, like you get really minimal striations. So it allowed us to like more easily like get volume calculations to, you know, be able to like make these assessments.
Hi, thank you for the talks, everybody. I have a question for Seth. I was wondering what, if any, effect you think tidal cycles had on the rift process that you observed, and if you were able to see any seismic signatures from tidal cycles.
That's a great question. So that is one area that I still have to investigate a little bit with regards to the Pine Island stuff, but my 2019, I think, paper was about a non-propagating rift on the Ross ice shelf. And in that case, we did observe that fracture was corresponded basically to tidal tilt. So in a sort of diurnal scale, the timing of rift events within a day was related to the tilt of the ice shelf, assuming that there's some extensional stress essentially exerted when the ice shelf tilts downwards. I think, you know, the sort of broad trends that we see here related to ice dynamics, I would say that tidal forcing probably isn't the sort of first order effect in terms of when within the year we see seismicity and when we see propagation of the rift on sort of a broad scale. But it could be that within the day, there's still some modulation of the stress due to tidal tilt. But I don't off the top of my head actually know what the magnitude of tidal tilt is at Pine Island Glacier in comparison to Ross, where the other one is. But that's a great question and something that we're going to be looking into soon.
Hi, my name's Elena. Great talks, everyone. My question's also for Seth. So you were saying that based on these seismic signals that you have, you can locate the source of the rift initiation. And the example you showed, it seemed like the source was upstream, and I was wondering if there's, because I'm interested in like polynya dynamics and how maybe, you know, these polynyas at the ice margins or at the shear margins can maybe initiate some rifts. So I'm wondering if you've seen sources near the margins at the ice front, or if it's mostly up glacier.
I think in the figure I showed, maybe it wasn't completely clear the orientation. Most of it was coming from the shear margin sort of on the calving front side, as well as near the rift tip. So in fact, like of the 50,000 or so catalog events that we recorded, maybe around 2/3 were coming from the shear margin. Which in some ways makes sense, because if you look at imagery of Pine Island Glacier over that period of time, there's tons of fractures that initiate in that period of time and grow in various sizes, whereas the rift, despite being large, is just one fracture. So even though it grows substantially, it's, you know, only a single source. So we do observe quite a lot of these flexural gravity waves that are generated in the shear margin. None of the ones that we've recorded presumably resulted in large-scale rift initiation, because at that point I think that the sort of main rift was already concentrating stress effectively enough that that the shear margin cracks didn't necessarily grow into a larger rift. But I think that this type of seismicity potentially could be useful in the future in terms of monitoring initiation of new rifts from the shear margin.
Great, thank you.
Thank you, I appreciate it.
Thank you guys. Thank you all. Great talks. My question's for Eliza. So do you think that your work on basal thaw could also be relevant to paleoglaciological data, especially when using paleoproxies for temperature?
Yeah, so in what area are you looking at?
Ross Sea.
Say it one more time.
Ross Sea.
Yeah, so I think that the basal thaw process is something that, could happen at any time. I have been looking at, my models initialized with modern day data, but I think that this type of process can definitely have happened in the future in the same way, and potentially impact that area. But I haven't looked into any details there. I'd be happy to talk to you more afterward, though.
I have another question for Jeremy. So you were talking about how important it is to consider the lithology and the topography. So I'm wondering if you have any ideas on how to integrate a very variable topography with some of your abrasion fandates, and then how that could possibly be scaled to a spatial scale that could actually be resolved in some models in the future?
Yeah, so with our laboratory apparatuses, we can try to add in some different bed forms and shapes to look at how that would affect basal friction. However, it is kind of difficult to scale it, using a smaller idealized geometry to what you'd actually see in Thwaites, where it's kilometer scale landforms. Yeah, so that's definitely a challenge about using the laboratory experiments.
I have 5 questions for Dougal. So when does frozen fringe become basal ice? How transient is that accretion onto the basal ice? And how might frozen fringe impact how water drains at the ice sediment interface or within the sediment?
Yeah, so that's kind of a part of this these experiments that we're going to be sort of interrogating further. But generally, sort of the rate at which that fringe is growing is dependent on kind of the heat flux and the temperature profile in the ice. So there's going to be spatial heterogeneity, kind of based on thawed, frozen, what the geothermal heat flux is, all that different factors. And generally there's an ice saturation profile. So moving downwards into the fringe, at the very lowest extent, right, you have some sort of ice water mixture in the pore space, but not completely ice. And as you move further up in the fringe, you get increasingly more ice saturation with thinner films of water surrounding these sediment grains, and that decreases permeability. So there's relationships between the permeability and ice saturation rate, and that the rate at which that's growing and how thick it's going to get, and at a particular heat flux or temperature condition is kind of related to these specific environmental variables at the bed.
It follows on really nicely, which is combining all of this basal work and these details about what that basal contact looks like with Eliza's work. Is a frozen fringe going to make places more or less susceptible to thaw? And when we start to get these more complete and complex models of the basal environment, what does that do to this theory about big purges of ice?
Yeah, so fringe, fringe can grow in both freezing and melting conditions, although it's, in freezing conditions, there's a threshold point where it kind of only grows transiently, and it's, can reach steady state in melting. But, it's really, I think, interesting, as you start developing these more, intricate maps of the bed, getting, as you, start constraining the bed properties, hard versus soft versus, thawed versus unthawed, kind of like developing, like in my mind, like the ultimate goal is like if you can like develop some kind of like spatial, scaled map of Antarctica and then try to get, a constraint on both like, the rate at which this fringe is growing and how thick these layers might be. Because it has a lot of impact, for like thinking about, such things as like, building up these like, these grounding zone wedges, right? Like the, that rate of deposition and the contribution of these like, these frozen fringe layers. But yeah, I think, kind of future work moving forward.
Yeah, and just adding on to that, I agree, like spatial maps of that would be a really interesting thing to incorporate into large-scale ice sheet models. I currently don't have a hydrology model or frozen fringe incorporated because we don't have that at the continent scale. So if products like that existed, that would be a really interesting thing to look at and add on more to be able to kind of explore more what these thawable, near-thaw regions are and how they might evolve in the future.
I had a question for Eliza. You mentioned that you used modern conditions. I was curious if you looked at any of the recent thinning of glaciers, like in the last decade, and if you did, if that had any appreciable effect on where we see a thawing bed versus a frozen bed.
Yeah, I have not. I think that's interesting though, and that obviously the thinning could change the basal thermal state. I think in some of those cases, thinning could cause refreezing because of less pressure at the bed, but there's also the component of acceleration as the glacier speeds up, which can cause frictional heating. So kind of looking at that trade-off and which dominates in terms of changing the basal thermal state would be interesting, but is beyond what I've done so far.
Question for Eliza, and I'll be very quick. Is your work dependent on your choice of sliding law? Is your work, like how sensitive is it to your choice of sliding law?
Yeah, good question. So what I had shown is results with a Weirtman friction law. I also did the same experiments with bud sliding, so including effective pressure. And I got similar results in terms of how the friction coefficient distribution differed in frozen, thawed, and thawable, and that pattern was consistent. So that's the most that I've done to expand the sliding law and see how that impacts the results. But obviously, I mean, the big elephant in the room is there's no temperature in the sliding law. So all of these are ways to try to get at the role of thawing, increasing sliding without actually being at the point yet in large-scale models that we have temperature in the sliding law. So when we are able to incorporate more advanced sliding laws that include temperature, include frozen fringe, include different types of geometry or, adaptive sliding laws, then this analysis will be interesting to look at in that context.
Like to note that there was a bit of a discussion online related to Nick Golledge's talk, and I haven't been able to keep up with it all, and I assume it's actually recorded so that people can go back and look at it later. Yeah, but it had to do with the ice shelf stability and the atmospheric forcing versus oceanic. Are they separate or are they additive? And there are some reference to papers, so I encourage you to go and look at it after the meeting. Okay. And I think it's noon now, so let's thank all the speakers and everyone for the session.